So shall we just start?
Sure. Let's start.
Oh, okay. So hi everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all very much for joining. Today, I'm very honored to introduce our distinguished speaker today, Professor Jianqing from Princeton University, at which he is currently the Frederick L. Moore 18th Professor of Finance and Professor of Statistics in the Department of ORFE. So over the past 30 years, Professor Fan has made many fundamental contributions to different areas of statistics, such as non-parametric statistics, high-dimensional statistics, statistical machine learning, and econometrics, as well as many other related areas, such as finance and economics. He has won roughly whatever prizes could be won by a statistician, such as the COPS Award and the Guy Medal in silver. He has also supervised many students and postdocs who have become leaders of different generations. He has authored or co-authored over 200 articles that appeared in many prestigious journals, and has authored or edited many books as well. Besides, his latest book, Statistical Foundations of Data Science, will be released later this year. Today, he will talk about statistical inference on membership profiles in large networks. Please join me in welcoming him.
Thank you, Roland, for a very nice introduction. So it's my great pleasure to give a talk here today. I should say good afternoon, or good evening, or good morning, or even good noon, wherever you are. Thanks. I know COVID-19 has a huge impact on the way we live, but I'm pretty sure one day we'll defeat the virus. And when the virus is gone, I hope this format of seminar will continue. So it's a very good way to communicate ourselves. But of course, I do not hope it will be a replacement of our person-to-person seminar. So I hope that one day I can eventually see you again in some conferences or in the seminar, or see you at Princeton. So my talk today is based on statistical inference on membership profiles in large network. And this is joint work with Ying Fan, Han Xiao, and Jinqi Liu. So we started like 4 years ago, or around 4 years ago. It takes us quite substantial amount of time to complete it. At the end of the day, I'll give you the reference. So I like this series called Mathematical Foundation of Data Science. As Joran just said a moment ago, that we working in the past 10 years or so on a book called Statistical Foundations of Data Science. Very similar to the name, and it will be coming out soon. And I teach a class here at Princeton, also named the Statistical Foundations of Data Science. But anyway, so these are the three lovely co-authors I mentioned a few minutes ago. So both of them are from business school, looks much sharper than I am. Anyway, so this will be what my talk is, introduction. I'll introduce the model, and then I'll talk about network inference in homogeneous setting, and then the under heterogeneous setting, and finally illustrate by numerical results. So let me begin with introduction. So we definitely live in a networked world, right? So citation network, social network, trade network, economic network, banking network, finance network, regulatory network, you name it, right? So all of these, if we abstract them in a simple way, we observe a relationship, right? A matrix. And in this particular case today, I will assume is adjacency matrix, which I have n by n, 0 and 1. 0 means two individual person connected or networked. Sorry, 1 means network and 0 means not networked. Just like this political block network that I'm drawing here. So each elements in the each node, right, representing an individual member. And after you running clustering algorithm, like a spectral cluster like this, political block network, my question today is very simple. how to quantify the uncertainty that a given pair of nodes are indeed in the same community. So this is a very simple question. Unfortunately, we have not good answer yet to this question. So here is a very simple example just to illustrate the idea and the products what I'm going to talk today. And this is one of the canonical data used in network studies, right? A very small toy example is a university club network data, which consists of 34 members. And the edge indicates that 2 members spend much of time together after club meetings. So in other words, they spend social hours, right, after the meetings were over. And at one point, it was believed that the club was split into 2, one led by Mr. H and the other led by Mr. A. So this is the network that we get. Now, if we community detection is really, a clustering based on binary data, 0 and 1, right? So after we run in, let's say, stochastic block model, spectral method in stochastic block model, we partition, the community into 2 groups. Right. So now, of course, people say, well, this is not the only method you can use, stochastic block model. We could use a different model, like let's say mixed membership model. At the end of the day, you may get a clustering like this, right? So now the question I ask is let's say membership number 7, Mr. 7 and Mr. 8, are they in the same group? Is Mr. 7 and Mr. 9, right, where somewhere in between, are they in the same group? There's uncertainty in our clustering. Or Mr. 7 and Mr. 10 here, right? Are they in the same group? So this is really the question I'm asking. So I really put in those together. Can we quantify the uncertainty of the links? So do these 2 persons really have the same membership profile or different? Right. So this is the question I'm going to address today. So at the end of the day, I was hoping that I was able to provide you statistician or data scientists in general. I'm very familiar concept, p-value. Right? So the p-value between number 7 and number 8 in the same group is pretty high. So we have no evidence they are from different groups. Number 7 and number 9 actually pretty small. Right, the evidence they are in the same group is pretty strong. Again, they're in the same group is pretty strong. And the number 7 and number 10, a little bit weaker, and so on, right? Now, the question is, how do we, quantify these p-values? And then, of course, the next question people may ask, how do I care? Why do I need to do this, right? So one thing, if you really study, like, let's say, other model, let's say, network-based model, people tend to assume within the same group, the parameter has some kind of homogeneity. So therefore, when you have certainty group people into the same group, like a network autoregressive models and so on, so you are going to assume homogeneity of autoregressive coefficients. So therefore, you reduce the dimensionality. Right? So it also help you understand and infer about network centrality and so on. Okay, so this is the question. How do we get in p-value today? And of course, this kind of application really go beyond just network data, right? So for me, being a professor of finance, as introduced by Joran, indeed, I'm also a professor of operation research and financial engineering, and a professor of statistics, right? So for me, there are very often, probably is more often than so, is I observe financial returns day by day, right? So I got a vector of financial returns of, let's say, Russell 3000. I have 3,000 stocks, right? And in finance, we believe that there are common factors that drive the dependence of market up and down, and then there are idiosyncratic components, which is genuine belong to that company, right? And of course, in statistics, we assume either sparsity on sigma u, the covariance of this u, equals single components, or sparse precision matrices, right? So more often you observe data like this, and this certainly have application to financial data I just mentioned, and to micro-arranging expression data, or apply to neurosciences and so on. Now, my question is, can we also infer about the network? Let's say a financial network, or can I do, let's say, the sector classification? Because nowadays, right, we know that Walmart is harder to quantify Walmart as a retailer company, or as what, right? Amazon in particular. It could be any, or Apple, could be many companies, right? So in other words, how do I do sector classification based on the return network, rather than based on quote unquote experts? Can we do this based on machine learning kind of methods, right? So in this case, I assume the sparsity of this sigma u is generated by underlying network or graph, right? So this is really the modeling. You're thinking your precision matrix is related to the graph Laplacian. So therefore you can learn about graph Laplacian, and through graph Laplacian, then you learn what I learned today. So in other words, your observed data doesn't have to be directly a network data. It could be just financial return data. And based on financial return, I want to quantify the sectors, the communities among financial sector data based on their returns. So this would be a very interesting and broaden the applications. So of course, there's a huge literature, and there's no way I can talk about this. All of you could put in your name under these dots, because there are lots of those. But to my best understanding, even the hypothesis testing here is not talking the same hypothesis testing as we are talking today. It's usually asking, are there any three group or four group, right? So this kind of hypothesis testing, rather than testing, are the two person really in the same community, so that I can assign similar, let's say, sector inference to the finance. All right, so now let me begin with a more, technical content, right? So let's begin with the review of membership models, right? So this is the common first version of model for model network is Stochastic block models. So in which I assume there are K communities, right? C1 up to CK. And if I have ith person belong to community K, jth person belong to community L, then the probability of they link each other is PKL, right? So this is the only assumption. So in other words, everybody within the community are permutable, right? Because their probability is completely determined by this edge probability matrix, right? Which describe, right? People within group have probability here. Let's say here is P11, here is P22, like this is the second group, right? And then between these two groups is P12. This is basically that edge probability. Well, here I assume everybody is permutable, but we know that within community, some people are more active than the other, right? So therefore, the probability of ith person knows jth person, given ith person in the kth group and jth person in the lth group, in addition to the probability of two communities average linkage, right? So I also have popularity belong to each individuals, right? So theta I and theta j describe the popularity or of individual person, the heterogeneity of individual person. So this is what we call degree corrected model. So in other words, this is a, let's say, 2x2 matrix. Now I multiply a diagonal matrix to it, right? And in particular, we all know that if all PIG equal, that is a random graph, really community disappear, right? So it would be called Erdős-Renyi graph, which popularly used as like a white noise that we use in statistical model, random noise, right? Okay, so this is a Stochastic block model with degree corrected, right? So now as I show here, in between Republican and the Democrats, right? So there are some people may be bipartisan, right? So 30% Democrat, 70% Republican, right? Somewhere in between. So this leads us to go further to the mixed membership, model. So mixed membership model basically assuming rather than just conservative and liberal, they are somewhere in between, right? In addition to black and white, they are gray colors. So here we assume that a particular person, node I, or a particular individual belong to a community with certain mixed probability, right? This person is 30% conservative, 70% liberal, right? So this pi ik, describe the this pi ik describe the membership profile, right? So here I just assuming there are only two communities, just like the image, right? We have three colors, right? So it could be a mixture of three communities, right? Mixture of four communities. So in general, I assuming that each individual is a mixture of K communities, right? So in other words, I have K communities, they are pure node. And in addition, I have other people is a mixture of those K communities. So this pi I would be an individual-based mixed membership profile. And in particular, if you have, let's say, coordinate, right, pi I just equal to 1 at the nth indices, right, and the remaining are 0, you really just saying the ith person belong to the nth community, right? So this would be a very special case. Our special case is just pi I equal to, unit vector. In this case, it would be the mixed membership. It would be just pure membership. And for today's problem, I'm considering this kind of hypothesis testing, right? Theta I equal to theta j. Is ith person and jth person belong to the same group? Or ith person and jth person doesn't belong to the same group? How can I quantify the statistical evidence between these two? So this is the first that we were trying to quantify. Okay, so now let me just quickly review what is really observed data, right? So our observed data is X. X is a binary response, right? Either ith person and jth person are linked or are friends or networked, right? And I assuming Xij, if since it's binary, I assume it's independent, right? Bernoulli with probability Hij, right? It's depending on which individual I and which individual J. Now is the time to specify what is Hij, right? And this Hij for the mixed membership model is as follows, right? Given ith person in the kth community, jth person in the nth community, the chance they network each other is depending on how active the ith person is, right? How active jth person is, and what is the average linkage between these two communities, P, KL, right? So, and this, I denote this P, a very small matrix. For today, I assume this K is unknown but fixed. Okay, so this is the probability, right? So this is this is the probability matrix describe the average connection between kth community and nth community, and this is degree of heterogeneity. Okay, so therefore the edge probability where we observe, right, Xij equal to 1, that's the only thing that we observe, right? So the edge probability using just, Bayesian formula, right? So it would be just summation of all this, right? So in other words, theta I, theta j, then the community, the community could be, I could be belong to kth community, J could be belong to nth community, and you add in these together. Right? So this looks a little bit complicated when I write into elements wise, but if I put in them into a matrix wise, it's very simple. So here's our model. Right? So pi is an M by K matrix. Each row talk about membership. Profile each individuals, right? So pi, each row is describing which member, which group you are in. And you observe is this X, right? So your observed X is equal to this H. H is this probability, right? And this probability from this model is, right, membership, which one? Right? So this is like pi, P and pi transpose times theta. Theta is the diagonal elements, right? Describe the heterogeneity. So in other words, our observed data, right, this is mean. This is observed data is equal to the mean. Mean is this, right? Probability mean is Hij. Hij have this kind of low rank structure, diagonal matrix, n by k matrix, or rank n or k, of course, and then k by k matrix, and so on. Right? Okay, so this is my observed data, and then W, of course, is the difference between X and its expected value, which is called generalized Wigner matrix. So is independent on the up triangle. Right? So throughout today's talk, I assume number of community K is finite but unknown. And of course, this includes stochastic block model as a special case. In that particular case, this pi, this theta are all equal, right? In either it would be a multiple times identity matrix. And in this case, all those pi just equal to unit vector, right? Coordinate vectors. Okay, so this is the model that we have. We have observed data contain this low rank matrix plus generalized Wigner matrix. Okay, now let's talk about the simple case, right? So the network inference under degree homogeneity. And because degree homogeneity, I assume my theta is equal to 1 parameter times identity matrix, right? So this is degree homogeneity. And now in this case, my expected value, my observed data's expected value is equal to this H. H will be equal to theta times this low rank matrix, right? And if you are willing to really write it out, I mean, this is just elements where I write it out, right? So from here, immediately you can, and the question we are asking is whether pi 1 equal to pi 2, for example, right? Whether these two pi are equal, whether those membership profile are equal. So this is the question we are asking. So it could easily seen from here or from just permutation arguments, right? So what is the difference between 1 and 2? They are exactly permutable, right? So therefore, the observed matrix that you have expected value is H, right? So if from here I could easily see the eigenvector, the top k eigenvector of this H is the eigenspace of this H, right? Is the same because this is n by k is really the same as column space spanned by this pi. So in other words, if you do orthogonalization of this pi, you'll get into this eigenspace, right? Because of this special structure. So therefore, the statistical inference I would like to make becomes, it was on pi, right? So now becomes on H. So really the inference I would like to make is on H. And because of exchangeability between pi 1 and pi 2, let's say suppose they are equal, right? So it's really become testing whether the ith row and the jth row of this H are the same. So this is the way that we bypass the identifiability. So for this reason, let me introduce some quick notation, right? So I assume this H, the expected value of this probability matrix, will have this singular value decomposition or eigen decomposition, in which D is a diagonal matrix and it's of rank K. So therefore, I have at most K non-zeros, right? I assume exact K non-zeros. And let me use V1, the first column, right? V2, the second column, Vk are the top K associated eigenvectors. And as I said a moment ago, because of exchangeability between the members in the same group, right? So if pi I equal to pi j, then the ith row and the jth row of this V would be the same. Right? So our problem becomes testing the eigenvector of ith row and jth row is the same, right? And in particular, this let's say suppose original have M communities, right? So pi I have M clusters. Then by these arguments, by this the second bullet points here, right? Then VM should have also M clusters, right? And this justify the community, K-mean algorithm people often use to do community detection. So in short, the question that we would like to ask is become very simple, testing whether the ith row of my matrix of my eigenvector V equal to the jth row of my eigenvector V. And now these people say, hey, this is easy. I have sample version. So let me begin with sample version, right? So sample version is my adjacency matrix, whose expected value is equal to this H, right? So I also have singular eigen decomposition. And of course, these eigen value may not necessarily of rank K. It rank could be as big as N, right? But anyway, I'll just choose the top K, right? So in other words, I'll let V1, Vk be my top K associated eigen vectors. And now my inference, my test that is very natural. I say, hey, based on the ith row of this V hat, and the jth row of this V hat, right? So this leads naturally to the following test statistics. So if you want to test whether pi I equal to pi j, this is the same as the V, the singular vector, the eigenvector, the ith row equal to the eigenvector of jth row, right? And this a natural test, because I assume K is finite, so without any sparsity or without anything that I assume with it, so a natural test would be Hotelling T type of test statistics. So in which we know the ith row and the jth row are highly correlated, right? So say that one would be the asymptotic variance of the difference between these two rows. And this actually probably the reason take us many years to develop the tool to do this, right? So it's quite challenging to derive, but nevertheless, we were able to derive it. So let me just put in here, theta I, theta j is coordinate vector, unit vector, right? W is generalized Wagner matrix, which is the original X matrix, right? And V is singular or eigenvector, and D is eigenvalues, right? So this is, you'll see it's quite complicated, but let for now, assuming it's known to you for now, right? So this would be a test statistics. Naturally, you may say, hey, what this test statistic would converge to, right? So this is still dependence. You need asymptotic normality and so on and so forth, right? So in order to have this, we always need some conditions. So one of those conditions is the eigenratio has a gap, right? The eigenratio has a gap, and the degree has to go to infinity in order to have enough data. And then we assume this pi matrix is have eigenvalue of order k, and then this the minimum eigenvalue of this p by k matrix is bounded away from 0, and then we assume some condition on this. I mean, the average degree theta 2, and so on, right? So and then we assume this is bounded away from 0. So this is basically the assumption we made, and this alpha m measure the sparsity of network and so on, right? So so this is our assumption, and then what we can really show is the following, as you expected, but it's quite challenging to show, right? So under the null hypothesis that the ith person and jth person belong to the same community, Tij, which is Hotelling T test for the ith row and jth row equal, right, is asymptotically chi-square distribution with degree of freedom k. So this is the first one, talk about the null distribution size, and then the second one talk about the power, right? So if under contiguous alternative that this guy hold, so long as pi I and pi j sufficiently apart, then this test would go to infinity. In other words, they will have power 1. And if you want the more precise description, so if pi ij is of this order, right? Of this order, 1 over square root of theta, then the test study will be asymptotically chi-square distribution with degree of freedom mu, right? And mu is pretty much the parameter that you expect to have. So this is basically described under the ideal setting, what is the test statistic, what asymptotically goes to. And now the question is, I have to estimate those in reality, right? First, I have to estimate K, the number of pure node, right? And secondary, I need to estimate this covariance matrix sigma, right, is highly complex here. Yoshio is very complex, right? Now the question is, what is this precision I need? And here the following theorem tell you what is the precision you need, right? So precision basically saying K had to be consistent, and then the sigma one, the asymptotic variant covariance, should have this kind of rate of convergence. So long as this rate of convergence, hold, then our plug-in statistics, right, will have the same property as you would like to see. Now, then the next question people naturally ask is, how do I construct an estimator of K, the number of pure node, and how do I estimate this asymptotic covariance, sigma 1? And so it turned out K is very easy because we are assumed have spiked eigenvalues. So you could easily just making using asymptotic theory, just making a test that say, hey, the eigenvalue bigger than maximum degree by a log n order, 2 times a log n order, and that's it, right? So that would be your estimate of K. And now if you want to estimate sigma 1, well, boy, you have to work it out, complicated asymptotic elements. An element turn out to be like this. It just show you complicated, but so right, it depends on the population eigenvalues, right, and depending on this eigenvector, right, A and B, this A and B entries, right, of this eigenvector, K's eigenvector and A's eigenvector and B's eigenvector, right? And then sigma ij is the variance like this, right? So anyway, it's very complicated. I don't expect you to remember. Just know that it's a challenge to derive this. That's probably enough. Of course, the good thing is, right? Individual variance here is, the individual variance is very hard to estimate because I don't know which one is community. But on the other hand, is averaged. Right, so the thing that is averaged here. So naturally, I will substitute this by the square residuals, right? So this would be leads to the following estimator, right? So this is X, right? So this is your singular value, the top K eigenvalue, right? The difference between this is your residual, and then you just substitute the square in, right? So just putting here as the square elements here. So this is a very natural. You use square residual as an estimate of the unknown variance, and the unknown variance will be averaged out. Right? This is very natural. However, this is not good enough. And the reason it's not good enough is we know that top eigenvalue is overestimated. So the bias is not negligible, right? The second eigenvalue is also overestimated, and so on. So top K eigenvalue generally overestimated. So therefore, we need to correct the bias, right? Shrinkage down, right? So this is really what we do. So first, you calculate the initial, right, residual the way that we suggest here, right? And now you just do bias correction, do shrinkage through this way, right? So this is WK0, that what we have here. This is K's eigenvector, this is K's eigenvalues, right? You do this way, so you got then a bias corrected version. And now you use this, right, to forecasting the residuals. Now you just replace these unknown one by the square residuals, right? And then you get what you want. And here's a formal statements. Of course, you don't expect me to prove anything here, but it's highly complex. But that can be shown. That K hat is consistency is relatively easy. So this requires some efforts to show that you really have the required accuracy for the for the asymptotic variance. And this, therefore, we will have a critical, region, right? We have right power, right size, and then the power goes to 1 like this. You will have asymptotic, chi-square distribution, and so on. Okay, so this is the first part of results is under degree homogeneity. Now the second part, after illustrate the idea, is relatively a bit easier since now we have concept. So all I really need to do is how do I knock down the degree heterogeneity, right? So the idea is easy. Mathematics is no more easier, right? So this is under degree heterogeneity. In this case, this theta, everybody has individual degree of, of popularity within the community. So you have this theta here, and this is your matrix. Now the first thing is I need to knock down these two so to make it homogeneous. And this is observed very nicely by Jianqing, right, in his 2015 paper. Introduced a procedure called SCORE, right? But it's not very easy and not very hard. Take you just 2 seconds if you have time to do it. But this, if you want to knock down the degree of heterogeneity, a very easy way to knock it down is taking the eigenratios. Okay, so the second eigenvector divided by the first eigenvector, right? This components by division. Third eigenvector divided by the first eigenvector. The kth eigenvector divided by that. So once you divide by that, so in other words, you take eigenratio, the kth one divided by first one, kth one divided by first one, right, for each elements. So you could easily show that the two persons belong to the same membership profile, have the same membership profile, if and only if these eigenratios, right? So column-wise division, eigenratios, these vectors are the same. So in other words, we are now become testing just eigenratio equal to the same rather than the other ones, right? And it would be a natural test statistic you would base upon is just do one extra operation. The eigenratio, one extra operation here, right? So once you get the top k eigenvector, rather than using directly testing ith row and jth row, you do division all normalized by the first eigenvectors, right? And then just comparing the remaining, the ith row of this y and jth row of this y, right? So we just lose 1 degree of freedom because we use one of those v's to do division, to do normalization, to knock down those degree heterogeneity. So this create an ideal test, right? For pi I equal to pi j, it become a test rather than based on original eigenvector. Now it's based on eigenratios, right? The ith row and the jth row eigenratios. And this sigma 2, of course, would be asymptotic variance of this, and the asymptotic variance of this now getting even more complicated, right? Depending on the variance covariance of these v's, and these v's is very ugly. And to be sure the formula at the end of the day is correct, require simulation to verify it, right? So this is a complicated formula. But anyway, so here is some common conditions. I assume each community has at least m member of order m member, right? And then this is the degree, how sparse the network can be, and so on. The remaining assumption is pretty standard. Then we can show that this test statistics under degree heterogeneity, because we do eigenratios, right? So we lose 1 degree of freedom. So it would be the asymptotic chi-square distribution, degree of freedom k minus 1. In addition, we know the power b equal to 1 so long as the second eigenvector of these guys is far apart enough. The test will go to infinity. And similarly, if you in our previous work, we all assume sigma is known, right? This k is known. Of course, in practice, I have to estimate k, and I have to estimate this sigma. So long as they're being estimated with this kind of required accuracy, the result I show you in this CM3 continue to hold. So this basically showing you that the asymptotic normality carries. Now the question is, how do I estimate this sigma? As I say, estimate k is not hard, at least under our technical assumption, because they have k spike eigenvalues. Estimating this sigma is hard. First, I have to see what this sigma's elements, right? Sigma 1 I even haven't shown you, and this is the sigma's elements, okay? So the typical elements of sigma 2, the AB elements, would be looks so complicated, right? So you will give up, right? So first, depend on the eigenvalue of the kth a plus 1's eigenvalue of that asymptotic distribution, right? And this eigenvector sigma kj is the variance of x jk and so on, right? So sigma is the variance of xjk, the Bernoulli random trial that you have, xjk, JIL, right? So this is depending on this T I haven't introduced it because it's very complicated expression, but basically is the first order of this dk. Dk is the kth eigenvalues. So in other words, this is the empirical kth eigenvalue, and this is asymptotic mean expression. This is all included here, but nevertheless, it's very complicated, but nevertheless can be estimated. And we can show that this estimation is asymptotically consistent, so that you could get a real statistics and with the estimated k and so on. So now here is a very small remark, right? So if the problem is homogeneous, but you can nevertheless treat it as heterogeneous, right? And in this case, method continue to apply, but then it will not be as efficient. So we'll see this in the performance. So in other words, if you knew it's homogeneous, but you want to be insurance afraid of bias, you do using heterogeneous procedure G here, rather than the procedure I say T before, right? G is for heterogeneous, T is for homogeneous. Then you'll lose power. We'll show this later. So now let me illustrate this just by a few numerical studies. So in these numerical studies, we actually have 7 membership group. So K equal to 3. So I have 3 pure nodes, right? And then the other 4 are a mixed membership of those 3 communities. And so I assume the network have 1,500 stock or 3,000 stock, like roughly 3,000, right? I do 300 simulations. My significant level control at alpha equal to 5%. And then these are the theta, right? So the average degree that we are using. So the bigger the theta, the more data you have, right? And then so this is for discrete heterogeneous case. We assume we simulate theta I inverse uniformly from this region, and this is the theta. So in other words, the order of magnitude on average should be similar to what we show you here. And of course, sigma 1 and sigma 2, even if you want me to calculate population, is highly complicated. We'll estimate those from the data, so that the test statistic is really the test statistics. And here show you some power and the size, right? So this is the case, n equal to 1,500. And then when I calculate the size, right, so I need to specify 2 members, right? So pi 2 member, pi I and pi j, are both equal to 20% group community 1, 60% group 2, and 20% group community 3. Right? So at this, so as we see that the size is pretty close to 5% for the homogeneous case, and then power, of course, as you can see, when the data increases, right? So degree of theta increases, average degree increases, this go to 1, 2, right? So the power is computed at this, right? So the now is this, alternative is this, right? Okay. Again, this pure node. Now, of course, if I do, let's say, for a degree heterogeneous case, as we said before, you'll lose a little bit power. Of course, you'll also lose a little bit size distortion too. You'll have slightly bigger size distortion, but the size getting closer to 5% as we getting closer to 1, right? And so on, right? And then power decreases a little bit compared to this. And the results similarly and a little bit better if you go to 3,000 case, right? So this is again talking about power size at particular location, and power is again these 2 communities comparisons. And now here is, I'm always puzzled whether the formula that I showed you before actually correct, right? Because it's so complicated. So we therefore just simulate our distribution when n is big enough and data is big enough. So for the homogeneous case, in this case should be chi-square distribution with degree of freedom 3, right? So this is the theoretical chi-square distribution, and this is empirical histogram based on 500 simulations, right? So it looks plausible, and we are happy. It looks very close, right? Now, if for discrete heterogeneous case, I use Gij. The formula very complicated. Again, in this case, it would be chi-square k minus 1 is equal chi-square 2 distribution, right? So it's like exponential distribution. So this is theoretical one, and this is the empirical one, right? So looking at these two formulas, well, the formula I show, and look at this simulation, the formula that I show you before is believable. So it's close enough. And this is just show you again for unknown k and size and power and so on. And then basically what we show is that when you have degree homogeneity, it's easier to estimate. There's no underestimate. So this is selection consistency. And then for degree heterogeneous, usually we slightly, when sample size is not big enough, we slightly underestimate the membership. That's why you can see we were using 2.05 in order to satisfy mathematics. If I can use 1.95, probably even better, right? Okay, so now the last one, I basically just illustrate this by using, let's say, political network data. And in this case, we are concerning about 105 political books sold online in 2004. And then in this case, the link represent that the book is co-purchased by the same buyer, right? So if the book's buy by the same person, you're adding a link to it or adding a proportion to it, right? And then the book has been, labeled by, Professor Newman into 3 categories, right? Conservative books, liberal books, and neutral books. Of course, this label may not necessarily correct, right? Now the question is, based on that network data, can we label just the same, similar to Newman's one using our hypothesis testing? Right? As I said, the label that provided by Newman may not be as accurate, and being argued in the literature, probably is better rather than only 3 categories, maybe conservative and neutral, and then there's many, conservative and liberal, and then there are many degrees of mixture in between. So this would be another kind of mixed membership models. So in this case, I take k equal to 2 pure node, and the remaining is a mix between liberal and conservative. And in order to compare the result by Jing and Justin Jing and his collaborators, we take the same 9 books, right? So this is the same 9 books. Some are neutral, some are conservative, and so on, the same 9 books. And here is the result, all right? So I compare, let's say book 1 and book 2, are they in the same group, right? So our p-value is pretty big. So this means the same group, right? We have now 1 and 3 based only on the data, right? Based only on the linkage data, co-purchasing data. We know that they are in different group, p-value is pretty small, right? And this would be 1 and 4 and so on. So now what is the color code here, right? So the color code here basically say if they are the same group and you are the same group, you are doing correct. I use blue, right? If they are in different group, this group is, as I said, is not correct. It's just marked by Professor Newman, right? So in this case, right, I mean, this is also correct, right? So I give a red, right? So among those, only book number 6, based on our data and based on our hypothesis testing, we group them into a different group. Otherwise, they are really the same group. So this is for the first book is from neutral. The second book will have the similar result. I didn't color code it here. And the third book is conservative book, right? So these are from different group. So therefore, p-value are small. These are from different group. The p-value are small. So using our learning algorithm, using our p-values, right? So we basically could classify the book the same way as classified by Newman without actually reading the book. Right? So this is, and then of course, this is based on TIJ, the degree homogeneity. If I base on GIJ, I lose 1 degree of freedom. Then the consistency is much weaker than what I just showed you before. And of course, p-value provides you, or test statistics provides you a very nice map. Right? So here, this is a multi-dimensional scaling projection on 2 dimensions. Right? So this is basically showing you what is the distance, right? Test statistic distance between these books in the conservative group. Marked by Newman's label, right? And this is the liberal group, right? And then yellow is like a neutral group. Right? So this provides you some kind of distance by using p-value as test statistics as a map, right? You could project into 2 dimensions and give you an idea how close those books are, and this is really a p-value based statistics. So I know that my time is good time up, right? So let me summarize. So what I have taught you today, right? So first, to my best knowledge, our work represents a first attempt to address community detection with statistical significance. So in a short way, that we provide a p-value to quantify uncertainty between 2 members, right? Whether they are the same or different. So we propose 2 test statistics for equality of the membership profiles for any given pairs, right? So we have with degree homogeneity and without degree homogeneity, right? With degree heterogeneity. And our method doesn't really assuming that K is known, right? So our K is relatively easy to be estimated. So it's pivotal to unknown parameter K. And we provide theoretical justification of our results and illustrate the method with estimated K. So this is our first attempt. So certainly there's a lot of things waving here and there. It takes us 4 years or so, right? So it's time to wrap up. So luckily, both papers, one is the first one more on asymptotic theory, and the second one is more on practical. Both has been positively reviewed by our peer journals. So hopefully it will be published one day. And this is the book, the paper. The second paper is much easier, very close to what I'm presenting today. So we just finished at the end of the year last year. So but anyway, so they are on archive, all the paper on archive.org. Thank you very much, and thank you for your attention.
Okay, thank you, Professor Fan, for the wonderful talk. There have been over 1,000 people attended this seminar just now across different platforms.
So I hope I've been careful enough. Sorry, I only missed myself. Okay, great. Yeah.
Yeah. So maybe let's look at some of the questions raised in the Q&A section. So also feel free to post the questions on the Q&A section. So the first one asks that in smaller sample sizes. Well, also, Professor Fan, you can also have a look at the questions, which is at the Q&A section.
Okay.
And when you click the Q&A, you can see the column called Answered. There are 4 posts.
Interestingly, I click, it doesn't show anything.
Oh, okay. Never mind. I will just
maybe my machine or my technology or my machine. I don't know. Yeah.
So in the first question, it is that in smaller sample sizes, would we be okay with losing efficiency for an unbiased estimate of membership between members I and J? And this is in regards to using the method for heterogeneity, even if you know you have distinct group memberships.
Okay, so the question is that okay. So first of all, if it's heterogeneous and you use homogeneous procedure, we know it's biased, right? So you will not have a property you want. But if you know it's homogeneous and then you use heterogeneous, we lose 1 degree of freedom. So therefore it will not be as powerful. And then we will hope, and the only thing that it can be compensated is when sample size is big enough, right? So then you, by losing 1 degree of freedom, you buy your insurance. So I don't know if that's the question that they asked, but yeah. So this is the general case is that buying insurance is not free. So from our simulation, right? So if you believe it's homogeneous or nearly homogeneous, which you can calculate the degree, right? So if when you have the data, you could easily calculate the degree for each from each node. If the disk degree not differ by too much, then you should use homogeneous rather than use heterogeneous because you lose your power. Now, of course, then it's come with an interesting question: how can I test, right, whether they are homogeneous degree or difference? That would be a different topic we haven't studied yet.
And another question asks that, is it possible to test whether the membership probabilities of 2 nodes in one particular community are the same? That is, pi ik, the null hypothesis is that pi ik is equal to pi jk for a particular k instead of all the vectors.
That's very interesting. Yeah, I believe we can. And I believe, I think the technical results should be a special case of ours. I believe it would be like a T type of test or chi-square with degree of freedom 1. So in other words, the asymptotic normality we build up is based on 2K asymptotic normality or 2K random variables, right? Because you have 1K for one node, another K for another node. Now it's only based on 2. And I believe the result that we had before can be extended. Good question.
Another question is that, is that possible that the multiple comparison issues could exist in the method?
That's a very good question too. So far, we haven't done that yet, and that should be done, right? So what adding complication is the test statistics, Tij, right? So they are all highly correlated. And so how to, I believe they still have asymptotic joint normality. How to do this is a challenging, but in a concept level, right? You could do what's so-called factor adjustment, because I think these correlations strong enough, you may be able to get in factor adjustment. Technically speaking, yes. I think we could state more strongly that we have Barry Essen type of results. So the asymptotic normality that we actually use is uniformly in INJ. I think that part of the thing that we can, if we work harder, I think that can be done. Yeah. But we haven't done any of these yet. Yeah.
Okay. So we have another question is that, suppose the test shows that the data are consistent with H0, the H0, and are inconsistent with the minimal departure from H0 considered as of subject matter importance. Then does that mean that we need to take as positive support for H0 that is a mere consistency with H0?
Okay, so here is so if I understand correctly, this is a very interesting question. So the question is that so statistical significance not necessarily the same as practical importance. Is it the issue that was raised? Sorry, I couldn't read the question. Otherwise, I could read myself. Right, sorry for that.
It's a bit long.
Yeah. So, but my understanding, typically hypothesis testing is used, right, from time to time is we have some goal in mind that we just want to, we just want to check if we, if the, in other words, we just want to check if the assumption that we made are reasonable or not, right? So, I believe that, if you think, of course, when you do hypothesis testing, you also have choices of alpha that is significant level to choose that too, right? So if you think that they are close enough, particularly if you use for downstream analysis, you assuming, let's say, they are in the same sector, so therefore of industry, let's say, so therefore they have similar impact on the risk of the financial system. So you can use these kind of assumptions. You could make those homogeneity. So it's the testing of significance is, I think, is just a typical, is very similar to the typical use, right? So depending on where you would like to, to draw the difference between the, the null hypothesis and the alternative hypothesis.
Oh, thank you. So I also have two questions. The first one is that, is it possible to extend the definition of clusters by saying that suppose the node I and node J have pi I, have the distance between pi I and pi J, say, smaller than 0.01. Mm-hmm. We define them as being in the same cluster. Is it possible to extend to such a setting?
Mm-hmm. This is very interesting, right? So similar to the question asked before, both are very interesting. So this is really, very similar in the, it's like a sort of like in different regions in statistics, right? Sort of in that sense. Yeah, certainly you can extend, the null hypothesis a little bit. Again, depending on, since we have already power there, right? So if you make null hypothesis extend a little bit to say, let's say less or equal to square root n, or relate to n theta, the power that we were able to test over there, then that should be fine. So that can be extended. So in other words, you can widen the null hypothesis a little bit of in different region up to the degree that cannot be detected by the, cannot be the power, right? So it's, in other words, it's a smaller order than you are in the detectable power. You could extend that, but you cannot go too far. So, so this is very similar to even classical statistics, right? So when you test in null hypothesis two-sample test, you can make it in different region. But once you make in different regions too big, then the null hypothesis is no longer pivotal and so on. So a lot of new problem arises. But if you make small, that should be fine.
Mm-hmm. Okay, thank you. So the last question is that, so here the limiting distribution depends on the k, it's chi-square and with degree of freedom k-1. Mm-hmm. So, but k itself needs to be estimated. So my question is, what if we select a rather larger k, which is larger than the true k, and then does that hurt the power of the method?
Mm-hmm. That's a very good question. As we all know, right? There is no, free lunch. They're very good questions. The short answer is yes. If there's only 3 communities and then you use 5, right? The power will definitely suffer because you are adding 2 noisy dimension to it. So which will reduce the power. So the answer is yes. If you use higher, it will reduce asymptotic work. The rate of convergence still work, but the power will be smaller.
Mm-hmm. Thank you very much, Professor Fan. It seems that we are running out of time. So due to the time constraint, let's finish here. And please join me in thanking Professor Fan again.
So thank you all for attend, and thank you for organizing this meeting. It's really wonderful. I hope that continue. And if you need any support, I continue to support this series. Not doesn't mean I give a talk. Let's say being a professor, financial support, right, or whatever needed. But anyway, yeah.
Thank you very much.
Thank you. So it's great, and thank you all for attention. It's really great, so efficient. I hope that one day I'll see you and you tell me, hey, I was in your Zoom now. It would be great to hear. Thank you, and say hello to you, and best wishes to all of you and your family. Stay safe and productive. Thank you.
Thank you, Professor.
Thank you. And also thanks everyone for joining. We are looking forward to seeing you next week at the same time. So thank you. See you next week.
Thank you.
Thank you.
Thank you.
Thank you.